Physics chapter 24, magnetic fields and electromagnetism is what we are going to discuss. So we are going to, you can remember what we have learned so far in O levels and AS. The magnetic field can cause a current and a current can cause magnets. Then there are magnetic fields without the involvement of electricity. And they have fields just like electricity does. So these are some of the basics that you need to remember, and we will start off from there. So wherever there is a force of magnetism, or if there is a magnetic pole, there would be a magnetic field. So this magnetic field is always from north to south. That is another thing that you need to remember. From north it goes to south, as here represented here. Then you have seen in a bar magnet how the field is going to be, and if the opposite poles here, as shown here, if the opposite poles come together, it would have something like this. But if it is the same poles, then there would be a repulsion, just like this. There would be an area where there is no field. That is because they press against each other. So then magnetic field lines, they have these qualities. They come out of north and then go to the south poles, right? From north to south, as shown here, from north to south. Then if the direction of a field line at any point would give us the direction of the force that a free magnetic north pole would experience at a point. So then if there are many field lines close together, that means it has a very high magnetic field at that point. So obviously magnetic field here is going to be higher than that is here, right? Because the magnetic field lines are close to one another. Then electromagnets, what they do is, how it is formed is, when electricity flows through a magnetic material, a magnetic field is generated. It becomes a magnet. So there has to be an electric current. We use a coil so that we can have because there is a concentration of material, so that there would be a higher magnetic field. So this coil is also referred to as a solenoid. One end of the coil becomes a north pole and the other end becomes the south pole, and it acts as if it is a bar magnet. But there are some some factors that would affect this. That is, because there is electricity that is flowing through, we will have to know the directions of the flow of current, and then what is going to be the north pole and what is going to be the south pole. So usually we can increase the field of this magnetic solenoid by having a core in it. So if there is a ferrous material, that is, ferrous means containing iron, if it has an iron rod inside, then this when through the iron rod the current doesn't have to flow through, but through the solenoid the current will have to go. Then what happens is, this iron core itself will become magnetized and would produce a stronger field, right? Then a flat coil would have the same effect as well, right? Now this is what happens. Magnetic field patterns for a solenoid. This is a solenoid. So there is it is curled, but here we are talking about a single flat circular coil. So that will also have the same effect, a flat circular coil. So there is current going from one end to the other, and as a result there is a north and a south pole that is being generated. If we make unravel this electromagnet, that is if we make it straight, we get a weaker field. We can figure out how strong or weak magnetic field is by using iron filings, that is when you the dust, iron dust, or a compass. If we take a long current carrying wire, then we can make it into a solenoid and figure out how the solenoid would, the length of the solenoid would affect the strength of the current. So then we can describe how the effect is going to be depending on when we go further and further away. We will see that iron filings get arranged quite distant to one another. So as a result, it shows us that magnetism, the effect of the field reduces as we go further away. So then magnetic fields are created by moving charges, right? So when we talk about a wire, it is the free electrons that charge. When you talk about a permanent bar magnet also, we talk about movement of charges. The magnetic field that is produced is done by the movement of electrons within the atoms of the magnet. So there are atoms in the magnet. So these electrons, the electrons in the magnet will move about, as a result giving out a magnetic field. So this electron goes around this atom, which will be a small representation of a tiny current. So this single the electron will result in a magnetic field. So when many atoms combine together, they produce quite a significant amount of magnetic field. In non-magnetic materials, what happens is they still produce the fields. However, they cancel out the effects of each other. But in iron or other magnetic materials, they arrange itself in a particular order to enhance the strength of this magnetic field. So now you know how magnetic field is created. It is always due to the movement of a charge. Then the direction of the field direction is something that we have to we should be able to identify and find out. Now we have we know that it comes from North Pole and going to the South Pole, but there are mechanisms how to identify these things. So these are the details that we would have. Now you can remember inside the solenoid and around a current carrying wire, how to figure out the ends, and how to figure out the north and south poles are described here. We will be discussing this in detail using the grip rules. The right hand grip rule gives the direction of magnetic field lines in an electromagnet. So what we do is we grip the coil, so our fingers go around it following the direction of the current. So it follows the direction of the current. So as shown in here in this diagram, current is going like this. So as a result, our fingers also go in this direction. Then your thumb will point in the direction of the field lines inside the coil. So the thumb would show the direction of the field lines. So it goes like this, because the thumb is in this direction, it goes in this direction. So that means it will point towards the electromagnet's north pole. It will be pointed at the north pole. So it is the direction. So this is the north pole. From, you have to remember, from north to south only the field lines go, north to south. So this is the direction of north. I hope that makes sense and brings back memories. Then if we look at the ends, also we can figure out if you look at the end of it, we can figure out which pole it is going to be. Clockwise movements would give you, clockwise direction of current would give you the south pole, and anti-clockwise would give you north pole. You would be able to figure this out using this relationship. Then when you go to the right hand rule, what we do is we are talking about a current carrying wire. Now that would not have magnetic poles. So that is going to be a little bit difficult for us to understand, but using the right hand rule, we can figure out in which direction the pole, field lines are going to be. So we grip the wire with the right hand, then thumb should be in the direction of the current. Then the fingers, our fingers will curl around in the direction of the magnetic field, right? The right hand grip rule applies to a solenoid, then the right hand rule applies to a current in a straight wire. I hope you understand. If you don't understand, ask me questions. If you do understand, do question number 1 and 2. 1, 2 and 3 of course. Then we will, before writing the note, we will do this practical activity and also magnetic force. Now we know that a current carrying wire is surrounded by a magnetic field. This magnetic field will have the ability to interact with another magnetic field. So this gives to a force on the conductor. Just like the fields of two interacting magnets. If there is a current carrying wire surrounded by a magnetic field, right? So there is a current carrying wire. When there is current flowing through a wire, we know that magnetic field is generated. So this magnetic field will interact with another magnetic field. That results in a force being generated. So we are going to figure out how this comes about and what are their effects. So this principle is defined by Fleming's left hand motor rule. To predict, we can predict the direction of the force on current carrying conductor. So let's figure out how it is, how we can figure out using a practical activity. So now in this 24.9 you know, diagram, we have thumb to show the motion, first finger to show the field, second finger to show the current, and all three are, and also please remember that this is the left hand that we are talking about. So this represents the hand, and it represents the three factors that join together to give us the sense of the force that is generated as a result of being in a field. So then thumb gives us the direction of the motion. So that means direction of the force. First finger is the field, second finger is the current. So when there is a current going in the direction of second finger, a field will be generated in the direction of the first finger, and there would be a force generated in the direction of the thumb. So all these three are at right angles to each other. So please apply this situation to different questions that are given here, and figure out whether you can correctly understand the directions in which these things apply. Now, to explain how these magnetic fields work, we can use the understanding that we have about magnetic fields of the magnets and the magnetic fields generated by current carrying conductor. So we know that we saw in using the motor rule here, earlier which we discussed, we know that it can produce a force. So now here they have shown the external magnetic field of the magnets, then the magnetic field of the current carrying conductor, and then the combined fields to give us magnetic fields which are going to be connected. So here on the left hand side we have a magnetic field of magnets. There are two magnets. Then there is a current going into the plane of the paper, so you should be able to use the correct rule and identify in which direction the field is going to be. Then what happens is there is a force, because this field is generated within and around this plane. You can see that there is a combined magnetic field of like this, right? So that happens all based on the Fleming's left hand rule, right? So as a result, what happens is, if we think about this force in this one, what happens is this force will kick out the wire out of this system. This effect is known as motor effect because we use it in electric motors. So what happens is, when a current produces a magnetic field, it generates a field, and that interacts with another permanent magnet inside the motor, which results in the force that makes the motor to rotate. If you understood all these details, do question number 4. Let's write down a note on everything that we have learned so far. Write down magnetism is created by the movement of an electric charge. If a conducting wire allows current to pass through, that generates a magnetic field. In magnetic materials, the rotation of an electron around the atom, around the atom's nucleus, creates a small magnetic field which will add up to produce a large magnetic field. However, in non-magnetic materials, the magnetic field effect of one atom is cancelled out by the other. Leave a line, put a star and write down. The magnetic field is shown to be originating at the North Pole and being carried towards the South Pole. I think it would be best if you can draw the figure 24.2, all these 3 bar magnets, so that you can understand how it works. Then write down a coil, within brackets solenoid, can be turned into a magnetic material by allowing an electrical current to pass through it. This is quite similar to a bar magnet, and its strength can be increased by including a ferrous core full stop. A flat coil and a solenoid both would have similar fields, and please draw this 24.3 diagram. Draw a sketch of 24.3. When electricity passes through a straight wire, we can figure out its direction of the field by using the right hand rule. The right hand grip rule would give us the direction of the magnetic field of a solenoid. I suppose you can remember all of those details. If you have any questions, please ask me. Then Fleming's left-hand motor rule explains how we could identify the direction of the force when the field, when the field created by a conducting wire interacts with another magnetic field. Please draw this diagram and explain what they mean. Thumb motion, first finger field, second finger current. This is referred to as Fleming's left-hand motor rule, because motors work using this force as described in this rule. I think it would be best if you draw this figure 24.10 also to show that to show the motor effect. If you have any questions, please raise them. If you don't have, please answer all the questions up until 4.